Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. This is going to be the first video for Calculus 2, so before I dive into the content here, I have a few things that I want to note. The purpose of these pre-recorded videos is to foster remote learning at Salt Lake Community College. When learning through these video lectures, there's a few things that I suggest to keep in mind. First, if you have access to the lecture notes that I use in these videos, as you can see here, have them printed out and at the ready so you can take notes about the concepts by hand. If you just listen to the lecture but do not physically engage to at least some extent, then it will be a lot harder to retain the information. It is all about active versus passive learning, and it is always better to be active. If you do not have the lecture notes or you cannot find them, please contact your instructor so you can get access to them. Secondly, one of the primary benefits to this style of remote learning is that you can pause the video or rewind at any point. This may be obvious to some of you, but I wanted to make sure that it is clear that you should take advantage of this concept if something in the lecture is confusing or if I go too fast. Thirdly, if I do not explain something to your understanding, remember that there are other resources available to you, first and foremost being your instructor. There are a plethora of other resources other than this, so if you do need more assistance, be sure to reach out to your instructor first. Lastly, after finishing the lecture, I recommend trying your hand at the homework associated with the section. So for example, in this section, we will cover 6.1, so I recommend going into 6.1 after this, if there is any homework assigned for that. Once you have the material down, you want to be able to try it out yourself. It is as if I explained to you how to swim or how to ride a bike in depth, but you then neglected to try it out yourself. The information will not stick, and the same is true here. I can explain things all day, but ultimately, if you do not try it out yourself, it will all go to waste. However, I just wanted to go into those few notes, and with that said, I want to start into section 6.1, areas between curves. Now, this may be where you ended your journey in Calculus 1 at Salt Lake Community College, but I wanted to at least do a quick video recapping some of the stuff in 6.1 since we'll be starting with 6.2 and beyond. In 6.1, we were basically just talking about how do you find the area between curves. So first, let's do a couple quick examples of integrals just to make sure that we do know how to find a standard integral. So first I have the integral from -1 to 2 of x to the fourth minus 2x cubed plus 2 dx. This one's relatively straightforward. There's no tricks that we need to do in this case. We should just have to apply an integral to each of these pieces. If you want to, you can see these subtractions and additions between each term in the polynomial here, and you can set each up as integral themselves. However, at this point, since we do not see anything complicated with it, we should be able to go at it directly. So we will say that this one is equal to, and we're going to apply an integral to each of these pieces. The integral of x to the fourth will raise the power up to 5, so x to the fifth, and what that will then do is bring the new power, that 5, down, and we will divide by that. So I can set that up as 1/5 x to the fifth. Or you could set that up as x to the fifth divided by 5, however you prefer to represent that. I usually like to keep the value in front of the variable by itself, so I like to keep the coefficient separate, but to each their own. The next one is a minus, and that minus will stick, so I'll have minus. The polynomial, the x to the third, will go to x to the fourth, and then that power will come down, so we'll have 2 divided by that new exponent of 4. Lastly, I will have 2, which technically 2 is 2x to the 0, more or less is how you could think about it. And so there is an x term there, and we are going to increase that by 1. So that is going to become x to the 1, and then we have 2 divided by 1. We also have to keep in mind that we have bounds of integration here. We have -1 to 2, so I will say that I want to integrate this from -1 to 2. I usually indicate that I'm going to integrate, or I'm going to apply these bounds with a vertical line with the boundaries listed there. If I did not have these boundaries, what I would instead do is have a plus c to represent some unknown constant that could have been lost in the process of derivation. Okay, but in this case we don't have that, so I'll just keep -1 up to 2. I'll simplify this a little bit. We have 1/5 x to the fifth, 2/4 I can simplify into 1/2 x to the fourth, and then this is simply just plus 2x. And then I apply these bounds. The first bound I should apply is the top one, so the 2. I'm going to apply 2 to all of these values, and I'm going to keep that into a square bracket, just because for organization purposes. 2 into x to the fifth, 2 to the fifth becomes 32, so I'll have 32 divided by 5. Minus, if I do 2 to the fourth, that gives me 16, divided by 2 is a nice clean number of 8. And lastly, if I put 2 into here, 2 times 2 gives me a number of 4. Then I need to subtract all the values where I put in the second number for my integration, the -1. -1 into x to the fifth gives me -1. So times 1/5 will give me -1/5. -1 into x to the fourth will give me a +1, times -1/2 will give me a -1/2. And then -1 into x here will give me a -2. Now at this point I see this minus and all these values end up being minus as well, so I can just distribute that negative amongst all of these to make them all positive. Nice and convenient there. All right, putting things together, I see that I have 33/5, so I can combine those pretty nicely. I have a -8, a +4, which is -4, +2, which is a -2, and I also have another 1/2. If I put all that together, I can either calculate that with a calculator, or we should be able to do it by hand. I see a common denominator of 10. So 33 over 5, if I make that into a common denominator of 10, that would become 66. So that's 66/10. This one would be 20/10. And this one would be 5/10. So 66 minus 20 is 46, plus 5 gives me 51/10. Or 5.1. Okay, so that's the first example. Second example, I'll move that 1 a little bit so it's a little bit easier to see, 5.1. The second example is going to be a little bit more complicated because this one we have two functions really multiplied by each other. We don't really just have a polynomial, which are relatively simple. Here we have the integral of 0 to 3 of y squared times the square root of 1 plus y cubed dy. Now this is going to apply a concept we discussed in chapter 5, which is called u substitution, or just substitution. We typically say u substitution or u substitution because we're usually using the variable u, but you can use any variable you want. Variables, whatever. U substitution. This involves substituting one part of the equation as u, and then substituting the other part as the derivative of that. If I look at the inside of this square root, which is usually where we're looking for a u substitution, if I set that inside as u, so I set u to be 1 plus y cubed, if I take the derivative of that, I would get derivative of 1 is 0, and then derivative of y cubed would be 3y squared dy. In my integral, I see that inside of the square root is u, but I also see that on the outside here, that is du. So I can instead rewrite this entire integral. Instead, I could say the integral of 0 to 3. Let's see if I could do some colors here. Of y squared, and that dy I'm going to set as du. And on the inside, I still have that square root of 1 plus y cubed. I can instead rewrite this, making sure that green part is du, as the integral of the square root of u du, otherwise known as the integral of u to the 1/2 du, because that's what square root is, exponent of 1/2. Now you'll note that I kept the bounds empty for now. Sometimes the way that some people like to do it is to integrate this and then substitute u back in for what it once was, the 1 plus y cubed. That is good to have if you do not have bounds on the integral. In this case, we do have bounds, however, so instead of solving and then resubstituting, I should be able to just solve for my new bounds and use those instead. So if we have 0 through 3 were my values of y, and I plug that back into u of 0, so the lower bound would be 1 plus 0 cubed, which is 1. And then if I plug in 3, I get 1 plus 3 cubed. 3 cubed is 27, so this becomes 28. So now the bounds are 1 to 28, 1 to 28, and I no longer need to resubstitute when I finish my integration. Okay, now to solve this, the integral of 1 to 28, u to the 1/2 du. Since that's just a single term, technically this is like a polynomial. This is just a single variable to an exponent. All I need to do is increase that exponent by 1 and then divide by what the new exponent becomes. U to the 1/2 would become u to the 3/2. And then if I divide by 3/2, so 1 divided by 3/2 from 1 to 28, that becomes 2/3 u to the 3/2 from 1 to 28. Therefore, my answer becomes, if I plug in 28 first, I can actually take out 2/3 because I'm going to be multiplying each of these by 2/3. 2/3, if I plug in 28, I get 28 to the 3/2, which is not going to be a nice number. And then minus the other term, which is 1 into here, I get 1 to the 3/2, which is just 1. This one is not going to be too terribly nice, and depending on the situation, this actually might not be too bad to leave it here, maybe eliminating that 3/2 and keeping it like this, because this is a nice and simplified term. If you need to find a decimal approximation of this, though, you can, and that would be 28 to the 3/2 minus 1 times the 2/3, gives me approximately 98.11. If you were to approximate that to 2 decimal places. However, personally, particularly from my classes, I think that this is a better answer because it's more exact. It doesn't require any rounding. Okay, so that's a couple examples of just how to do some integration. So hopefully that reminded you. Hopefully it wasn't too long since you last did some. Okay, so the rest that I have here on this page is a lot of terminology and a lot of definitions that we'll be using. In Chapter 5, we defined a definite integral using Riemann sums. What that means is that we looked at the area of a region, such as this curve. We looked at the area of that region by finding rectangles to approximate that area. Something like that. That would be the process of Riemann sums. However, when doing that, as you even see when I drew this, there are some pieces of this integral, of these rectangles that I drew, that are a little bit higher or possibly lower than the shape that I'm actually trying to find. So this would actually be an over-approximation. And there are ways of doing different types of Riemann sums, either the left side or the right side or even center. But either way, they always approximate. And what we tried to do was trying to progressively increase the number of subintervals that I have. So instead of just having these 1, 2, 3, 4, 5, 6 rectangles, I would maybe divide them up again into equal subintervals. So maybe now I have 12. And that should get better because now I'm going to reduce the amounts of error. This is either represented as having n go to infinity, where n is the number of intervals that you have, or having delta x go to 0, which implies that the width of the interval, which is delta x, is getting smaller and smaller. You sometimes see limits represented as going from n to infinity of this, and this is, I think, how the textbook that you have tends to go, but sometimes you'll instead see a limit of the delta x going to 0. It's the same process. They both mean the same thing. But overall, that is the limit that we use to try to come up with the definition of an integral, which is taking the function from bounds a to b, where a is your lower bound and b is your upper bound. That is our definition of an integral. We will use this definition a lot to come up with a lot of our other definitions moving on. The whole process of a limit of a sum of these rectangles. If we can come up with something using that terminology, then we can translate that into an integral, which is usually what we want to do. Now, if we're trying to find the area between two solids, so something a little bit more complicated, something like I have a curve here, it actually should be between two curves. So a curve here and like a curve here, and I'm trying to find the area there. Well, that's a little bit more complicated if I'm trying to find this area, because now I'm not just trying to find from a curve down to an axis or a curve over to possibly the y-axis. What we're instead trying to do is trying to find the area between these two. And to do that, we're going to try to find the difference between the two curves. So the upper curve minus the lower curve, typically. This is usually represented as, say, function f being the top curve and g of x being the bottom curve in a general sense. And therefore, we get this formula instead. Note that it's the same process. The only difference is that instead of having f of x sub I, we instead have f of x sub I minus g of x sub I. That would be the difference of the two curves. That will give us now an integral of a difference of those two curves. Nice and simple. We can apply the same concepts if I instead have a curve defined with the variable y, so x equals f of y instead of y equals f of x. I could do that same process thinking about subtracting the rightmost curve minus the leftmost curve. Both of these general definitions are for if you think about it in the first quadrant, I'll say. So here I have f of x being the top and g of x being the bottom. So this is like if you have a curve, two curves like this. This top one would be f of x, the bottom one would be g of x. And we would find the slice here by subtracting f of x minus g of x. If I was instead doing slices horizontally, something like I have a curve here and a curve here, and I'm trying to find this slice, well then I'm going to take the rightmost curve, f of x, and subtract the leftmost curve. Another way of thinking about this is that if it's the concept of the furthest curve minus the closest one. And we are always thinking about that in terms of whatever integration axis I'm working for. So if I'm working for y, then that means I'm looking at the y-axis and thinking which curve is furthest away from that. Likewise, if I'm working with the x-axis, if you see x here, then I'm thinking about which curve is furthest away and then which curve is the closest one. I say that more generally because these curves could be elsewhere other than the first quadrant. They could be in second, 2, 3, or 4, and then you want to think about which one is furthest away, which one is closer. But let's do a couple examples so you can see this in action. Okay, first, find the area between e to the x and sine of x from 0 to 2 pi. The first thing you should do for all of these is try to graph them. And for the most part, a lot of these you should be able to graph from algebra. You shouldn't need any software. You shouldn't need to look up anything in terms of how to graph these. Particularly these two curves, e to the x and sine of x, you should know how to graph those. Both of these from 0 to 2 pi, that means we're in the first quadrant. So 0 to 2 pi. Well, actually, we're going to be in quadrant 1 and 4, really. E to the x starts at 1 and increases exponentially, hence the name. So e to the x runs like this. And sine of x, if you remember from trigonometry, sine of x starts at 0, increases up to 1 at pi halves, decreases down to 0 at pi, decreases down to -1 at 3 pi halves, and up to 2 pi. So sine follows this general pattern. And now what we're going to try to find is the area between these two curves. So from 0 to 2 pi. Note that in this case, e to the x starts at 1 here and increases exponentially, so it has no chance of intersecting with sine, where sine equals 1, because sine equals 1 at pi halves. So by that point, e to the x is already above it. Therefore, we don't need to make multiple integrals because they don't intersect. If they did intersect, then we would have to cut it up at that point and create multiple integrals. However, here we should be able to set this up pretty simply by considering our slice. If this is a slice that I'm working with, in this case, the curve that's furthest away from the x-axis, since these are both defined with x's, the curve that's furthest away from the x-axis is e to the x, and the one that's closest is sine of x. So this should be e to the x minus sine x. So we'll set this integral up appropriately. We'll have that the area equals the integral from 0 to 2 pi. That's my bounds of integration for the x-axis, 0 to 2 pi. We need these bounds because they're defined with the x variable. The furthest one from the x-axis is e to the x, and we subtract away sine of x. We also need to make sure we include at the end dx. Now, some people may point out this area down here where sine of x actually dips below the x-axis. That's actually not a problem. That would be a problem if I was just trying to find the area of sine of x, but since we're actually trying to find the area between these two, that will actually not be an issue because this will actually find the difference between wherever e to the x is and wherever sine of x is at any of those points, and it will take those distances. So actually, we don't need to worry about that. Now, this is an integration that we should be able to apply pretty nicely. The integral of e to the x is a very easy one. That's e to the x. And the integral of sine of x is also pretty easy. The integral of sine of x is negative cosine. So that gives us plus cosine of x. We're also making sure that we're going from 0 to 2 pi on this. All right, well, we can plug in 2 pi everywhere. We have e to the 2 pi. That's some number that can't be nice. Plus cosine of 2 pi. Cosine of 2 pi, that will give us 1. And then if I plug in 0, I get minus e to the 0 plus cosine of 0. Cosine of 0 is also 1. And so is e to the 0. So really this is e to the 2 pi minus 1 overall, because this would be 1 minus 2 to give us negative 1. All right, e to the 2 pi minus 1. Or if you want to find that as a decimal, e to the 2 pi minus 1 gives you 534.49. However, this answer, again, is better. It doesn't require a calculator. It's more exact, etc. Next example. Find the area between y equals negative x plus 4 and y equals square root of x from 0 to 6. Okay, 0 to 6, that implies we're working in at least quadrants 1, possibly 4. We have to graph these to see where they are. Okay, so let's... Okay, there we go. Let's just make a standard line. We see negative x plus 4. Okay, well, that means that it does go up to 4 on the y-axis, but that means it is also going to cross over the x-axis, at least at some point. And it should go down to negative 2 by the time we get to 6. Negative x plus 4 starts here. It's a straight line, and it goes to 6. It would hit this point. So I have a straight line, something like this. That would be negative x plus 4. Now if I graph y equals root x, and I'll do that in blue, square root of x starts at 0, because square root of 0 is 0, and then it increases like a parabola, but towards the x direction. That would be the area that I'm looking for. I'd be looking for the area in between these two, so there and there, and then also the area from here to here. What that means, however, is that I have a point right here that I need to find, because in this case, when I would try to subtract the quote-unquote top minus the quote-unquote bottom, that's going to change when I hit that point. From 0 up to this point, I have that negative x plus 4 is the top function, and the bottom function is the square root of x. But then past that point, square root of x is the top function, negative x plus 4 is the bottom. So I need to find the point where they intersect, and I can do that relatively simply by setting them equal to each other. So let's do that. I have square root of x equals to negative x plus 4. That's a little bit hard to solve, so let's square both sides. I get x squared equals, if I square this side, I get x squared minus 8x, and then plus 16. And then, oh wait, nope, that's that first one is just an x. Square root of x squared is just x, okay? And then I subtract x on both sides. I get x squared minus 9x plus 16 equals 0. Okay, that one's a little bit hard to solve, so in that case we can do quadratic formula to solve that, or to finish it off. We can set this up as x equals negative b, which is 9, plus or minus the square root of b squared, which is 81, minus 4 times a times c. A is 1, C is 16, so 4 times 16 should give me 64. Divided by 2A, which is just 2. So we get 9 plus or minus the square root of 81 minus 64, that's 17 over 2. Now we're going to get two values. The reason is because square root of x technically continues on like this, so it is going to intersect somewhere later on, but we're going to look for the lower x value. So in this case, if we solve both of these, probably the subtraction, if I look at 9 minus root 17 divided by 2, I can approximate that. 9 minus square root of 17 divided by 2. And I get about 2.44. Let's do better than that. Let's do 2.4384. More decimal places, the better. Usually 4 sig figs. Okay. And then we can solve using that situation. We can say one integral is going to go from 0 up to that point of 2.4384. And between those points, the uppermost function is negative x plus 4, and the bottommost is minus the square root of x dx. Then we have another integral from 2.4384 up to 6, where the upmost function is square root of x, and then we subtract the other one, which would be plus x minus 4 dx. We could set up these integrals. The first one is going to be, I'll do in square brackets, would be negative 1/2 x squared plus 4x. And the square root of x we did earlier, that would be minus 2/3 x to the 3/2. And that is going to go from 0 to 2.4384. And then we're also going to add the other integral, which is 2/3 x to the 3/2 plus 1/2 x squared minus 4x. And that one is from 2.4384 up to 6. So kind of sort of get squished there, but those would be the two integrations. And then at that point, you're basically just plugging in each of those values, which is more of a plug and chug at that point, so I'll leave the rest to you there. Okay, so yeah, just leave the rest to you there if you want to plug in those values and approximate this. This would come out to be some ugly decimal. There's not really much of a way to simplify it further. But yeah, so you would integrate both of those. Last one, we'll find the area enclosed between x equals 2y squared and x equals 2y plus 4. Okay, now these some people have trouble with because they are in y. They're in terms of y instead of terms of x. However, that shouldn't be too bad. You just have to think generally what they mean. 2y squared, that's going to be a parabola, but it's going up the x-axis instead of up the y-axis. And 2y plus 4, that's going to be a line. And if you need to solve that, you can subtract 4 divided by 2. You get x divided by 2 minus 2 equals y. So you can also think about it as a line like that. Either way, let's draw both of these. Okay. So 2y squared. 2y squared is going to be a pretty sharp parabola, so it's going to be something like this. That's going to be 2y squared. And we'll actually continue since it's a parabola. We'll continue like that. And then if I graph either x equals 2y plus 4, which means that intersects the x-axis at 4, or if I have it as x over 2 minus 2, which means it intersects the y-axis at negative 2. Either way, I can graph that and I get a straight line like so. There we go. All right. We note that it did not give us any bounds. That means that this is an enclosed area, which means that they do intersect at least twice, or they should. And we can find where each of these are by, just like before, setting them equal to each other and seeing what happens. So I could say 2y squared equals 2y plus 4. We move everything to one side. 2y squared minus 2y minus 4 equals 0. And I can also divide everything by 2 to make this y squared minus y minus 2 equals 0. And this one, you can do a quadratic formula, or you can actually notice that this one can be split up pretty nicely. Both of these as y. Two numbers that make negative 2 would be 2 and 1. One of them being negative, and since I see that this negative y, that means the 2 should probably be negative, not the 1. So we have y minus 2 and y plus 1. That would create this quadratic up here. So that means that these intersect at y equals 2 and at y equals negative 1. So that means right here, y is negative 1, and right here, y is 2. And what we're going to do is we're going to make slices horizontally, where in this case, the furthest line at all points is this straight line of 2y plus 4, and the line closest to the y-axis at all points is 2y squared. So I have my direction for how to set up my integral. In this case, I would set up my integral as from my bounds from negative 1 to 2, since these are all in y's. And then I'd set up my furthest one as 2y plus 4, so 2y plus 4. And then I'd subtract away the closest of 2y squared dy. This is a nice and easy polynomial, so we could solve that. 2y becomes just y squared plus 4y. Negative 2y squared becomes negative 2/3 y cubed, and this being derived from negative 1 to 2. If I plug in these bounds, we get 2 into y squared gives me 4, plus 4y, that gives me another 8, so that's 12 overall. Minus 2/3 times another 8, so that's minus 16/3. Minus, if I plug in negative 1, I get 1 plus, or actually minus 4 it would be, so that's a negative 3. And then negative 1 into y cubed is a negative 1, times negative 2/3 will give me a plus 2/3, which is going to end up being subtracted anyway because of the distribution here. So overall, that gives me negative, or minus a negative 3 will give me a plus 3, with the 12 gives me 15. And then we have negative 16/3 minus another 2/3 will give me minus 18/3. 18/3 is otherwise known as 6. So if I do 15 minus 6, I get an answer of 9. All right, so those are a few examples, just a little bit of as a recap of 6.1. At this point, I don't think there's any homework set up for 6.1, depending on your instructor, but if there is, you should go and try your hand at that. With that said, I hope you have a great day.